Hello, I am Jennifer D'Souza, one of the co-organizers of this year's SemEval-2021 Task 11 NLPContributionGraph. My co-organizers were Zoran Auer and Ted Pedersen. In this talk, I will give you an overview of our shared task. So let me begin right away with the problem premise that motivated our shared task. Scientific literature is growing at a rapid rate. Approximately 2.5 million new papers are published each year. So researchers today are faced with a deluge of publications. It is increasingly tedious, if not practically impossible, to keep up with the research progress. In light of this, the Open Research Knowledge Graph project is a solution to the problem of keeping track of research progress, minus the cognitive overload that reading dozens of full papers impose. So what exactly is it? It is a next-generation digital library that aims to represent structured scholarly contributions in a comprehensive scientific knowledge graph. And a benefit of obtaining structured scholarly contributions, as you can see on the slide, is to be able to compute surveys automatically on the key characteristics of research. Which brings us to our shared task. Motivated by the availability of digital libraries as the ORKG, we designed the SemEval NLPContributionGraph shared task as a step in the easier knowledge acquisition of contributions for researchers. So our task essentially formalized the building of a scholarly graph over NLP scholarly articles as an automated task. So, the task was defined on a dataset of NLP scholarly articles with structured contributions annotations. The annotated data was provided as 3 different information granularities, including sentences, which were a set of sentences about the article's contribution, terms and relations, which were a set of phrases extracted from the contribution sentences, and triples, that were semantic statements that paired entities with a relation modeled towards subject, predicate, object, RDF statements for KG building. The triples themselves were organized under 3 mandatory or more information units, and we will look at what information units are a bit later. Thus, the end-to-end extraction task pipelined the 3 forms of data. Extracting triples relied on having extracted the scientific terms and relations, which in turn depended on extracting the sentences. So what was the overall graph structure? The NCG uses 2 levels of knowledge systematization. At the root, it has a dummy node called contribution, and below the dummy node, it has 12 nodes, generically referred to as information units. And what is an information unit? It is a construct to organize the contribution triples, analogous to sections in the traditional research article, as we will see by their naming schemes next. Research problem is one information unit in the NCG, where triples about the research problem are organized in this node. An example is contribution has research problem NER. Other information units could be approach or model, where triples about the solution proposed for the research problem were organized in terms of the system highlights. Now, here is an example of a research problem information unit with all 3 granularities of data, including sentences, the phrases that were referred to the research problem themselves, and triples. But the system outputs were expected in the following format. For sentences, we just expected sentence line numbers. For phrases, it was a bit more detailed, where we expected the sentence line numbers, character offsets of phrases from the sentences, and the phrases themselves. And finally, for triple annotations, merely phrases organized as subject, predicate, object triples. So on the slide, you see an example of a research problem annotated data, and here is a bit more detailed model triples annotated data. Our task data statistics were the following. Training data, we annotated 287 articles in all, And to be representative of the field, they were distributed across 29 unique tasks like NER, machine translation, summarization. Our test data had 155 articles across 10 unique tasks. Some more numbers in terms of the granularities in our data themselves: information units, thousands of sentences, tens of thousands of entities, triples, and subject, predicate, object elements in the triples. So what was our task essentially? We expected participants, when given a scholarly article in plain text format, to extract a set of contribution sentences, to extract the terms and relations from those sentences, and to organize the phrases as triples under 3 or more of the 12 IUs that we described. And their options for participation, well, they could participate in one or more of the 3 evaluation phases we had. Where in phase 1, we tested systems for the end-to-end task, and this was our main evaluation phase. In phase 2, we tested systems only for phrases extraction and semi-pipeline triples extraction, and in the final phase, we tested systems only for triples extraction. So in the final phase, they were given both contribution sentences and phrases as goal data. And they could participate on our competition site on CodaLab. So our competition was hosted on CodaLab, so system submissions could be automatically evaluated therein. And basically you see a bit of a system participation demographic. In terms of scoring, this is a snapshot of the results table on CodaLab, where submissions were evaluated in all granularities of the data, and within each granularity we used the standard F1 precision recall metrics, and the individual teams were ranked by 1 score that was an average of all the F1 scores. And so the results in our shared task in terms of end-to-end graph creation, the top team had an average F1 of 49.72%. The top 2 teams didn't differ too significantly, but the rest of the teams did. Sentences annotation saw a high score of 57.27%. Phrases annotation saw a high score of 46.41%. And the triples, the best performance was considerably lower than the previous 2 tasks at 22.28%, and thus proving as the hardest extraction element. Now comparing pipeline versus non-pipeline results for phrases extraction, we saw that in the non-pipeline setting, each team's score was boosted by at least 20 points. Similar pattern was observed for triples extraction, wherein given only goal sentences and automatically extracted phrases, the best score was 43.44, and given goal phrases in addition, the best score was much higher at 61.29%. We think that a score of 61.29 is a strong performance on a still fairly difficult task, given also the annotation decision subjectivity that may have crept into the data. For additional evaluations, we refer you to our task paper. So some observations: contribution sentence classifiers, basically 2 strategies: binary classification or multi-class classification. BERT was the most prominent approach, and the best stream strategy was indeed binary classification and BERT with additional features. For phrases extraction, we saw a mix of sequence labelers as a majority approach and heuristics. Again, in terms of sequence labelers, BERT with a CRF layer was the more prominent approach and also the best strategy. Triples extraction, we will look at just the top 2 teams. So the best team adopted 6 different strategies based on our dataset's characteristic, used a specialized trained BERT classifier for each of the 6, and obtained an overall score of 49.72. The second best team extracted all possible triple candidates, classifying them as true or false, and also used downsampling. In addition, they used adversarial training to boost individual system performances. And their overall score was not too different from the first team at 47.03. So the takeaway, what is the takeaway message? A view on scholarly communication. Not much has changed. We are still using the document-based format. It's changed maybe from books to PDFs, but it's still discourse-based. Okay, some things have changed wherein metadata is increasingly getting organized in knowledge graphs. However, in other domains such as product catalogs, they're entirely revolutionized on digitalized data. So the solution, we need structured research data, and the ORKG is one initiative advocating for this. So it basically focuses on making research papers structured mainly by crowdsourcing. And where does our task comes in? It is the first attempt to formalize the building of a scholarly contributions focus graph over NLP articles as an automated task, and thus can complement the ORKG's crowdsourcing. It has attracted a strong participation demographic of 27 participants and 7 teams. In the approaches to building the NCG BERT transformer models were popular, and however, the end-to-end performance was considerably low, showing the task as challenging, and the best system adopted a hybrid approach, which seemed the most effective strategy for building the NCG. Our task data is publicly available on Zenodo for researchers interested in the task, and a quick glance of the summary of our paper is also available on the ORKG itself. So thank you. Special thanks to the co-organizers of the shared task, Soren Auer and Ted Pedersen. Special thanks to all the participating teams in our task. Thanks also to the ORKG project and team. And last but not the least, thanks to the SemEval-2021 main event organizers. Here is our funding statement, and thank you too for listening to my talk, and I am happy to take your questions and answers now.